starting it. I hope it's recording. Yeah. So what's our plan? A quick logistics here, recap, right? So we have homework 5B, homework 4. Homework 4 due now, demos next few days. That is the neural network. Then we have homework 5A due, I think it's next week. I think that the purpose of this homework is that you guys have to do it before the Thanksgiving. Next week. As long as you have something submitted, and you could do the demos on that after Thanksgiving. But I don't want to pass the Thanksgiving holiday and not even start looking at that. So I'm going to force you to submit something before Thanksgiving, which means by Wednesday night. That is 8 days from today. That's easy, by the way. So homework 5A, it's not complicated. It's an LDA from library. We're going to talk about LDA today. Our next 3 lectures, our next big chapter here is the LDA and the sampling associated with it. But because this is a library call, you shouldn't have a problem with that homework. And then homework 5B, that will be obviously after Thanksgiving, that is implement your own LDA. That's a toughy one, okay? So I think homework 5B is the hardest homework in this course. So that's gonna, I hope you're gonna have a good Thanksgiving, because when you come back, we're gonna have to deal with that. Again, this is a little bit of functionality. So there's the very easy stuff. The not so easy but not difficult is the summarization that we talked about last time. So S, it's a summary of document D, and the way we did that, we want to minimize the KL distance between PD and PS, where PD is fixed distribution for document D, and PS, it's moving distribution for summary S. As in, as you build your summary, this distribution will change, and your target is to match this one. The reason we like so much LDA, kind of in sync with this, is because these distributions, you could do it over words, but it's better to do it over topics coming out of LDA. So instead of representing those 2 distributions over words, which will work too, it's a better way to do it over the topic. So we need to run LDA to get those topics first, and then we represent these as distributions over topics. We have to talk about LDA, of course. That's the plan, right? And then we're gonna do this, which is kind of our baby LDA implementation. It's not gonna be as good as the library call, but it will have all the kitchen ingredients that are needed for LDA. So that's our current plan. And like I say, we already looked at the final. It's on 12/12. It's either 2 p.m. to 8 p.m. or 12 p.m. to 6 p.m. Let's see. We're gonna see a piazza poll about that if I can move the room. All right. So let me start with the introduction. And part of that introduction, I'm gonna make a parenthesis at some point, because something I want you to know about, but as it happens, it's not that useful for our current purpose. But it's useful to have heard about it. So I'm gonna say, let's start with this idea of a term document, term matrix. So I'm gonna say, now we're talking only about documents, although this matrix is a general machine learning matrix. we're gonna say, okay, what do we have? We have x1, x2 up to xn. Those are documents. And then we have word 1 up to word D. Those are the words, right? And if we're looking at the data set, we may have 50,000 words and maybe 20,000 documents for different counts. So typically, term doc matrix or doctor matrix refer to, let's call it, I don't know, A. It's in these notes here. In here, if I have Xi and Wj, if I go to the cell Aij, usually Aij is some sort of count of word J in doc I, right? Sometimes those counts are altered. Sometimes it's called term frequency or term frequency normalize or TF, IDF sometimes. There's all kinds of machinery that people apply to those counts to kind of make them smoother, better, more suitable for probabilities and whatnot, right? But in general, think of this as a count. And this is a very sparse matrix. Unless I start making modifications to it, because a lot of the words do not appear in a lot of the documents. So most of them will be 0, apart from stop words, which appear in every single document. Right? But stop words, as it happens, they're not interesting at all. That's a term document matrix. Here's an idea. We want to factorize it. So I'm going to say, I'm going to think of it purely algebraically on the factorization. So I'm going to use K, the rank. K has to do with the number of independent rows and columns. And it's a very well known in linear algebra that if the rank of this matrix is 10, then it can be factorized into something that has internal dimension 10. So something like, I'm looking for some matrix that is n by k times a matrix that is k by d. Right, that's the last word, d here. And algebraically, we know this is possible. So back to linear algebra. If you look at the number of independent rows and columns here, and that happens to be a lot smaller than the matrix. Sometimes you have those matrices, 100 by 200, but the rank of the matrix is 15. That tells you there's 15 independent rows in there. The other ones are linear combination of those 15. That tells you that you can factorize it with only an internal factor of 15. That k could be 15. But it's easy to show that the rank of this product will be k or less. So if you try to factorize it with an internal k of 15, but the rank of this matrix is 25, that's impossible. Because in here, you're going to have at most k linear. If you do this product, you can have more than k independent rows or columns, simply because there is only k coefficients that act on k rows, on the k columns here. So if I do this, the maximum independence I can have is k, and that's always possible if this matrix had that rank k. But if this is a highly independent matrix of a rank higher than k, this is not possible. So people have looked at this and say, that's interesting. So can you take a term document matrix and factorize it? Well, obviously, we want to use this as a dimensionality reduction, because our new dimensions will be k. Every one of those documents will have k components here, and every one of these k components will be some representation into the original components, which are the words in here. So we kind of want to do two things here. We want to say, okay, well, for this kind to work in practice, so in practice, not exact. So we're saying, okay, it's unreasonable to think that such a matrix has a dimension like 10 or 15 or 20 or 100, because this matrix is much bigger than 100, right? And then we say, well, let's call this, they have a name here in the slides. Let's call this W and this H. I don't know why they picked those names, but so we want A to be approximative A times W. So we can hope to get it exact, but we want to like kind of like that product, W times H. So we have an error, which is sum for all cells of Aij minus WH. That's a matrix Ij. W times H is the matrix, that cell Ij. So I take all the differences between the cell that results as a product and the cell in here, and I square them, and I sum up all the n by d differences squares. That's kind of like the sum of square errors in there, right? So I say, okay, if you don't get it exact, that will be 0. Every Aij will be exactly that cell. Well, do the best you can, minimize this error. But the other thing is, we want W and H to be of positive values. So we want this representation, if I am to interpret this as still as quantities like counts or probabilities or anything that has a natural interpretation, if I ask for this decomposition as a pure linear algebra numerical decomposition, chances are some of these values will be negatives in there. That will make it work the best possible. And I would like to have a natural interpretation of components. So I'm adding a condition that I want positive numbers in there, but I'm relaxing the fact that they have to be completely equal. Saying not completely equal, maybe that's too much to hope for, and I probably fix k in advance. Like I want 100 dimensions out of this thing. So that's an idea. As it so happens, this is not the best idea for terms and documents. Terms and documents, especially natural interpretations, don't follow linear algebra rules. Like PCA fits very nice with linear algebra because projections are matrix multiplications. Rotations are matrix multiplications. All that sum of square errors and variance fits very naturally as dot products and so on and so forth. So the definition of PCA by longest variance axis and some rotations matches very well with linear algebra operations. But this understanding of what is the content of a document, if you like imagine every row is a document here, and those are the words. So in terms of describe a document into words by counts, it's not, especially in a very sparse form where most of them are 0, those play very badly with linear algebra operations. But if you really want to do this, let's say not for documents, because what I describe here could be done for any matrix, right? I take a matrix, maybe I have a dense matrix of features, and those are not documents, those are images or something, and then it makes more sense to do it. So as an idea of factorizing a matrix by k components, it's always possible if k is at least the rank of that matrix, but if it's not possible, we can do the best we can. See the best approximation with k independent components. This is called non-negative matrix factorization, NMF or NNMF. That's saying I want to break a matrix into independence of k as close as possible. That will be 0 if it's truly of rank k. But I'm adding a condition that will make it harder, that I want, assuming all the a is positive, all the counts are positive to start with, because I can have positive times positive to give me something else. Assuming that I want that to happen. So I'm not going to insist at all on the mechanics of how to do this. It's pure linear algebra mechanics. But I want you to know what non-negative matrix factorization stands for. You may hit this concept either with documents or with images or other things. It stands for a positive matrix that's decomposed into a product of matrices, where the rank controls kind of how many independent things we have. And we do the best approximation for this error. So now, as an idea for how to do it, start with some W and F, A and H, initials, and then do EM-like approach. EM, remember, I have two things, chicken and egg, and I'm taking one and optimize the other, taking this one, optimize the other, and I'm playing in between. Hopefully, at some point, I'm going to converge, hopefully. So here's how that works. One of the steps will be updating the H. So update H, CJ, I don't know why it's CJ. It's HCJ, that's a new one. HCJ new. Let's not put an arrow, let's just put equal. Is the HCJ times WTA So when I say CJ, I mean that cell. This is a matrix times that cell. And then that's one of the E&M steps. And the other one is update the other one, which is WIC new, is WIC times AH transpose IC. Again, that is the IC cell of this matrix. WHHT IC. Now, again, I don't want to do any linear algebra right now. So how did we get this? Doesn't matter. Some mathematicians, linear algebras, they got it. We don't want to be that ignorant, but for now, let's not focus on where they got these. But we could focus on one thing, just to see if this makes sense. What happens if WH is exactly A? All these EM rules or gradient rules, when you reach the objective, you're supposed to not move anywhere. So I think you can see that if A is WH, this is exactly that. So this remains whatever it was. And if WH is A, again, you can see that's the same matrix. So then update, I'm going to do nothing. So at least we can tell, hey, if you get close to the objective, these updates start being smaller and smaller and smaller, they don't do anything. The other thing that we can verify is the direction. If this is too big of a matrix, how it's H updated should be in the right direction. It should be increasing. And if this is too small, then H should be decreasing. And then, assuming this is all positive, so we want everything to remain positive at all time. We're not going to the negative side of things. Again, we're not deriving these formulas, but we can at least intuitively say it seems to going in the right direction from where you start, and if you're getting closer and closer to that objective, they get closer and closer to convergence. I think we could easily implement this, assuming you can start with a W and H that are reasonable and positive, then you can implement this. Like with every EM, there's a danger of getting stuck in a local, maybe optima. This is convex enough that maybe we don't have to worry about that. We can implement this. Again, this is cell by cell. So it may be tedious, but it's relatively simple. Every cell is itself times the ratio of how far away that matrix is from the what it should be. Okay? So that is, again, my interest in here mostly is a hidden agenda so that you see non-negative factorization if you ever need it. But remember, it's not so good for terms and documents, and especially sparse matrices. But it may be useful for other things that you want to decompose a matrix, especially the matrices that you believe have low rank. Because if they have low rank, this could be a very close approximation to it. Yes?
So, for example, what would be the initial value for W and H? Do we just make a matrix of random natural numbers and start, or?
That's a good question. How do we find those initial numbers? I think one of them can be random within a reasonable space, like probabilities, and the other one should be kind of the best. I think the way I would start this process is to get one at random, and the other one try to compute some quotients to see how close I get to that thing. But I don't think there's a sense of feasibility here. Like in a lot of like simplex methods, you need to start with a feasible solution. And here feasible means they have to be positive. So as long as you don't start with a lot of zeros or negatives, that should be fine. Yes?
What do W and H tell you at the end of the day? Like, where is your information?
So the way I think of this is my documents are represented with K components. So this
Okay.
W is my new representation. Every data point,
Mm-hmm.
image or patient or house or document is now written with a vector of K things as opposed to D things.
Okay. Oh, and those are
And
coefficients.
every one of those components is written as a vector of words.
Okay.
Right? So I want to think of this as K components, or maybe concepts. Sometimes for documents, we call them concepts. And the idea is that every document is a vector of K concepts. Vector, I mean K coordinates, that's K numbers. And every concept is a vector over D words. These are all the words. The D is the whole vocabulary. Like these are like 100,000 words or 500,000 words. So this is very useful for text. When you think of text representation into fewer dimensions than say 50,000 words, say I want to represent it in 300 or 500 dimensions. For 50,000 to 500, I'm talking about 1%, right? I'm talking about reduction of 100 times the number of dimensions. So in that sense, it's very useful to think, well, these 500 things, the new 500 things, let's put that K equal, let's be even more drastic, T equal 50, D equal 50,000. So I could easily have 50,000 words or more, but I want to represent everything in 50 new components, and for text, let's just call them concepts. So we can have concepts like religion. That's a gigantic concept. But we can have more refined concepts like Catholicism or Catholicism in Middle Ages. Very, very refined things. Another concept might be World War II. That's a lot of stuff about World War II. It's a gigantic concept, right? But we can have more granular concepts, like maybe the war in Pacific, World War II in Pacific, or maybe a specific battle in the Pacific, or maybe a specific general in the Pacific, like somebody who really did something specific. So that's clearly much more granular than the whole World War II. So I think we can define those concepts, and the idea is that every concept, it's kind of represented in words. Every concept out of the 50,000, every concept is 50,000 dimensions. But the bigger values indicates what words are related to that concept. So if my concept is World War II, well, I'm going to have things like atomic bomb, Douglas MacArthur, you know, Eisenhower, Hitler, you know, Germany, Nazism, those things. So that will be now related to the World War II concept. So out of the 50,000 words, those words will be appearing in the World War II concept with high counts, with high probability or high weights, right? World War II. So as an example, World War II concept will have high values on the words related to World War II. And then a document will have a high value on this concept. Right? This is one of my concepts. A document that's about World War II will have a high value on this concept. Does it make sense? Maybe I have another concept, diabetes. Now diabetes will have a different high words. Things like blood sugar and you know what you eat and you know obesity and heart problems, right? And then a document that has a high component on diabetes, that will be a document that talks about those things. So as a very very naive but extreme example, actually, let's look at this and say what would be three concepts here. I'm gonna put just three, right? Three concepts. This one is World War II, this one is diabetes, and this is Boston. Those are grand concepts. Sometimes they actually call that way, grand concept, because it's still a huge amounts of things that fit in there. Like I said, we may have far more granular concepts in practice. It depends how many you want. Like if you want 50, you have to have big granularity, but if you're willing to live with 500 or 5,000 concepts, then you have. So clearly this concept will be, if I look in here, those three concepts, right? The World War II will be related to things like Nazism and Stalin and Hitler and tanks and United States joining the war and all that, right? But diabetes will have high components on very different words. Diabetes will be related to blood sugar, to obesity, to heart problems, to you know genes conditions and whatnot. And then Boston will be related to very different words, unless somehow Boston is correlated to diabetes, but probably that's not the case. And then once I have my concepts, let's say I have 50 of them, so one of them in here might be Catholicism. Every document now will have weights on these concepts. So every document is a representation of K things, depending what's about. So this is a new idea where we have these abstract features that are not like PCA dot product of the original. Those concepts are not necessarily dot products of the original words, and are not like feature selection, like this homework tree you guys have. Pick the words that are most useful, because World War II in itself is not necessarily a word in there. It's just a whole concept that relates to World War II. So we're talking about semantic concepts, ideally. Like when we say something relates to World War II, it may not be written necessarily as Nazism or Hitlerism or Stalin, but it may be very well connected to World War II. So we're talking more like semantic concepts. But of course, semantic stuff is hard in practice. How do we know that that document is about World War II if it doesn't mention Hitler, it doesn't mention Nazism, it doesn't mention 1940s, it doesn't mention atomic bombs and whatnot. So that's a little bit of a tricky thing to do. So anyway, I started you guys on the wrong track here. That even though this idea as a linear algebra, as a data matrix can make sense in a lot of places, dense matrices that have linear algebra correlations in them may be suitable for this. But even if they are, big matrices will give you a hard time to do these kind of things. Like I mentioned this as regression, even though there's a closed form for regression with linear equations, normal equations, in practice you still do gradient descent to approximate that. You're not using the normal equations. So that may happen here. If I have I don't know, 1 million pictures, and every picture has, pictures are pretty big these days, right? So they're like 9 million pixels. That's a gigantic thing to deal with. Trillions and trillions of stuff. Not easy to decompose it necessarily. Now, of course, mathematicians are working very hard for how to do some of this stuff very fast, so I'm sure within mathematics, linear algebra, there are fast methods to do NMFs here. So I want you to know that, but what we really care about is this whole thing idea with concepts. So we want the concept part, but we don't think it's going to work with linear algebra. We want to do it differently. So, version number 2. Version number 2, I still have this matrix A. This is document I, and this is word J. And I still want two matrices. We can call them W's and H, or maybe I changed my mind. I don't know what's in the notes. And we still have K components here. That is true. So we're gonna call these K topics or concepts. But we don't want to do a linear algebra between them. So these are matrices. This is N times N documents. This is K times D, indeed. But the relationship we're looking for is not a pure product thing. The relationship we're looking for is probabilistic. We want every document actually, I think it's in here. So I'm going to say here, it's kind of like with probabilities. So it's not, this is not a dot product. In here, every document, so that's still xi there. Document xi is a distribution over k topics. So this is the k, these are the k topics I have. So that means the document xi in there will be like xi1, xi2 up to xik. This is a distribution probabilities that sum to 1. Every document is a distribution over topics. Every topic is a distribution over words. So that will be topic. I don't know how it's in the notes. Those things are called I think it's called phi. Topic phi k. So that will be phi k1, phi k2, up to phi k, I don't know why the k is on top, phi kd. So those are also probabilities. that sum to 1. So every topic as a concept is a distribution over words. Think about a topic like diabetes. We'll have high probabilities on things like blood sugar, heart attack, and obesity and whatnot. And think about these as documents that have high probabilities on diabetes as a topic or not. Or, like I said, they make good topics. World War II diabetes, Boston Catholicism. These will be so-called super grand topics. In practice, we probably need to be more granular than that. So that's what we want. But there is no product here, directly product. So we're not looking for an algebraic relation that says this matrix times this matrix have to give me this matrix. That's not what we're doing here. Okay? So this process, for various reasons, it's called latent Dirichlet allocation. Very fancy name. In fact, we'd be hard pressed to figure out even one of these words what it means, let alone all three, right? Latent Dirichlet allocation. Allocation probably has to do with probabilities, right? It implies probabilities. Dirichlet is the prior, it's a conjugate, that's called conjugate prior of doc word distribution. Let's forget about the word conjugate. You can erase it from your notes. Forget about it. We don't worry about that. It's the prior. Is then if somebody give me a distribution and I don't know what document they're talking about, on average, what do you think the distribution would be? Like before you see the document, right? So that is this prior. And latent is that once it's kind of backwards, right? This is a generative process. But we are reverse engineering it. Reverse. So I'm going to talk a little bit about generative process, but the reverse of it is saying, well, we know the document term matrix, right? Because we have it, 20 newsgroups, we know it. So from here, go ahead and figure out the topics. Let's call this matrix phi. Let's not call it that anymore. Topics phi, that's K topics. And the other stuff, what do we call that other matrix? We'll get to it in a second. And we figure out all the probabilities, right? It's called the Z, I think it's called. I have to see in the notes what it is. Doc probabilities, Z. So the reason I'm saying it's reverse is that as a generative model, here's how people think of generative models. If you give me the topics in some way, maybe I have more generators here. Maybe I have a fixed set of topics like this matrix, or maybe I have a source that picks topics from this matrix at random somehow. So here's a bunch of K topics, and I have somebody with a coin or a die roll that says, every time you ask me for something, I'm going to pick a topic at random. In fact, we should write that down. Here's what the generative model does. If I find the right paper here. So sample topic by K, it's the sample probability from that matrix phi. Phi beta is a parameter here. for each document sample doc parameters. I think it's called data. Sorry, I forgot. Data. And I think it has a parameter alpha. So sample, for each document D, sample this from the sample probability of alpha. And then for each word in document D, select topic let's call it this optional. It's too complicated to do this. Select a topic and then select word according to that topic. But this idea will generate words. Effectively, it says if you want a document with 100 words, for every word, we'll pick a topic from this chosen sample here, and then for that topic, once I go to the topic, I'll say, okay, produce a word with that probability from that topic. Once I know the distribution of that topic, I say, okay, pick a word with that probability. So if my topic happened to be diabetes, chances are the words that I'm going to generate is going to be something related to diabetes. But if my topic is World War II, chances are I'm going to produce a word related to World War II. So there are multiple, when I say sample, I think pick one at random. Sample in here means pick item, object at random according to probabilities. To distribution given. P1, P2, up to P, whatever, Z things. So when I say sample, I mean you have a distribution and you pick something according to those probabilities that are given to you. Now, so the difference is, this is a generative model or process. It's called model, generative model. That if you have this stuff, you can generate documents. Because every document, you go how many words you want, that's how many words I want. For every word, you select a topic, select so you first have to select the topic parameters, then the document parameters according to some probability. Say I want a collection that talks half about diabetes, 25% about World War II, and 25% about Boston. So that I fix some parameters. Then every time I need a document to say 50 words, I'm going to say, okay, for every word in there, select one of the topics with these probabilities. 50% will be World War II, 25% will be that, 25% will be that. And then once you have the topic, select a word from that topic. So if you pick the topic World War II, you're much more likely to get something like Hitler or Stalin or atomic bomb. But if you pick diabetes, you're much more likely to get blood sugar. So a document is a distribution over those topics. Topics are fixed in the generative process. So I have that matrix, every topic, what is it over the words? And every document is a probability over topics. So if I say 50% World War II, 25% diabetes, 25% Boston, for 100 words in that document, for every word I'm going to say, okay, pick one of those three topics, and once you pick the topic, pick the word according to that topic probabilities.
So I just had a doubt about, like, we'll know beforehand what the topics are going to be.
No. So I'm saying that's the, we're going to turn this on its head in a second. if I have the topics matrix, that is, here are my topics: World War II, diabetes, Boston Catholicism, and every one of them has a probability over words. And if you tell me what, for each document, what probabilities you want over the topic, so the document I just described, right? Document I just described might be 50%, what did I say? 1, 4, 1, 4, right? Because I have 3 topics here. But another document might be 0, 3/4, and 1/4. That means if my first topic is World War II, this document will not have anything to do with World War II. Does it make sense?
So like, how do we find out what the topics are going to be? We only have like a number
We're
of-
getting there.
Okay.
You're very impatient, okay? First, I want you guys to understand what the generative process is. If I have these topics, and for each document I know the distribution over topics, what does the generative process do? It goes over every single word on that document. It asks you how many words you want in that document. You say 50 words or 100 words, okay? It goes over everything and says, pick one of the topics. Now, these are random independent choices. Our language model is very much every word is independent, which of course is not true. If it talks about World War II, it's more likely to keep talking about World War II. But we're assuming a very simple generative. Anybody knows what IID stands for?
Something independent distribution?
Yeah, independent identical distribution of words. Of course, that's not how documents look in practice. They're not IID. But let's assume a very simple IID model. What the generative process will do, for every one of the words, pick one of the topics. So in this will be 3/4 this one, or 1/4 that one. And then goes to that topic, looks at the probabilities, and say with those probabilities, generate a word. That is, every word is going to be generated with the frequency of those probabilities. And it will do that for how many words you want in that document. Then it goes to the next document and say, that's a different set of probabilities. Therefore, for every word, it's going to say, okay, you have a 50% chance, 25 on these 3 topics. Depending which ones you picked, you go in there, pick the word for it. And the next word, and the next word, the next word. For each word, I select the topic according to the document probabilities, and I select the word according to the topic probabilities. That is, if I have these 2 matrices. Those are matrices of probabilities where the rows sum to 1. Right? But notice that there's no product between them. We're not making that. We are having a generative process that says, if I give you that, I can generate any amount of documents. I mean, for every probability distributions, I can generate a document. Notice that if I have another document here, 1/2, 1/4, 1/4, that's not going to be the same document as the first one. Each has the same distribution over topics. So as far as this representation is concerned, it's the same document. But if you were to generate it, you're not going to pick the same exact topic at every word. And even if you do, you're not going to pick the same exact word from that topic. It may be that on this document, the first topic being picked is the second one. It's 25% chance. And here the first topic being picked is the first one. And even if you pick the same topic at word number 17, from that topic, it'll be 50,000 words that you can pick a word from. So this generative process, on average, fits those probabilities, but it's actually instantiated. It's not just probabilities. When you generate things, you actually see a sequence of words. Over time, it matches these frequency probabilities, but that one particular document, it's whatever comes out from the generator. All right? So that's the generative process. Now, of course, we don't have these. We don't have these matrices. What we have is the final output. What we have is a bunch of documents that have been generated, presumably by a model like this. When we apply a model, we assume the data we see has been generated by a process like this. Of course, it's not true. the medical records or history records or whatever you want to call it, they've not been generated. Wikipedia is not written this way. But we assume there is a generative process that was like that. There are a bunch of topics, and each topic is a bunch of words. And the generative process generated my collection of documents, like 20 newsgroups, or Spambase, or Wikipedia, or whatever I have. So the reason I say it's reverse is because we are not doing the generation. If we have the topics and words and probabilities, we're not generating the documents. We're doing the reverse engineering. We're saying, if I show you the output, which are the documents with the words, can you figure out what topics and what probabilities were used to generate those topics? That's effectively the same way like we estimate mu and sigma in a Gaussian. We assume data has been generated by a Gaussian, which is not true, right? Or some other function. And then we say, what is the best mu and sigma that would have facilitated that kind of generation, right? So we estimate mu and sigma. That will be the best Gaussian to be used for generation to look like what we observe in reality, even though my data was not necessarily generated, in fact, by a Gaussian. So it's the same kind of principle. This will be my parameters of generations, like mu and sigma for a Gaussian. And I look at the final output of documents and words and distributions and say, can you compute the topics? I'm going to fix K for now. I'm going to say, let's assume I've used 50 topics. Can you generate the topics and the documents properties into topics? So those two matrices. Hands up who's with me. That's what we want. So we want the reverse engineering. Now, what's our objective? If I come up with two matrices, and he comes up with two matrices, and he comes up with two matrices, how do we know? Same K, everybody has K equal 50. How do we know which one is better? For a Gaussian, how do we know? If I get a mu and sigma, and if he gets a mu and sigma, he gets a mu and sigma, how do we know which mu and sigma are the best ones?
If we apply them, we get something that looks like the original.
Right. So the way we measure the parameters value, right? So the quality of, let's call it generative params, those would be the theta matrix with alphas theta depends on alpha. I'll discuss that in a second. And the phi matrix that depends on a beta is measured what? As a likelihood to generate the observed data. Likelihood, that's probability, right? So how do we know a particular mu and sigma for a Gaussian case is good? Which is the same as saying, how do we know two matrices are good? Well, we ask, if those are my two generative parameters, what's the chance that my generative process that does that, picks the topic, picks the word, da 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 da, what's the chance that that particular process generates exactly the 20 ng collection? Of course, those properties in reality are extremely small. No matrices will generate the 20 ng. The chance in reality, the property is 0. Right? You cannot expect to generate 20 newsgroups this way. But this is a model, so we can actually measure certain things and at least say, well, the properties are very small in absolute terms, but we know that some particular matrices look better than others. Right? So that's what we want to do. And guess what happens? In homomorphic Phi, we don't worry too much about it. We just call LDA in Python, and it's going to give us those two matrices. It's going to happen like this. Boom. Done. Yeah, so we should at least check the result that we are obtaining n by k. That's, again, the documents into k components. And another matrix that's k by d, which is every topic probabilities over the words. And this is implemented in all languages, LDA, latent directly allocation. That produces topic modeling. The whole story here is topic models. Notice that the numerical ingredients here are the same like in there, a matrix of size n by k and a matrix of size k by d. But we're not doing products between them and approximating this matrix. We're looking for this way to say the generative process associated with this stuff results in documents similar to 20 news groups, or similar to my patient records, or similar to my loan applications, or whatever documents I have. Of course, that requires reverse engineering. The way we do it, we look at actual documents, and we create the two matrices out of it. With this criteria in mind, what does it make to have two good results? Means that a generative process based on these particular matrices, it's better than the same generative process based on some other parameter matrices. So, that's a nice story. But what's needed here? There's a lot of stuff that's needed for homework 5B. Like if you are to actually do this, how do you do it? Like think about that there is a bunch of things that need to happen. It's true we have the output. So we look at, we have document term results, right? We look at any collection like spam documents of 20 news groups and say we can easily get this. But then how do we reverse engineering this particular generative process? So let me establish here a list of things that are required for this to work. So what we're gonna need is, so clearly we need, so LDA requirements. We need, of course, the term document matrix. That we're gonna call just data, or text data. That is the data set we wanna do topic modeling on. We also need K, and we need the initial parameters alpha and beta. We're gonna talk about that in a second. So we need to start from somewhere. But then, this is not necessarily procedural, this list. It's what I need to show you guys before you can do 5B. We're gonna need to first address the idea of what is a term document distribution. That exists somewhere in here. If I select a bunch of words according to topics probabilities, how do I model that? Model from as output of generative model. Because of course you can look at term document distributions and say measure term frequencies, divide by document length to get some probabilities. Right. What I mean is, if I tell you that's my model, I'm saying out of that model how documents probabilities would look like. Remember, I'm not talking about necessarily real documents, but documents that this kind of model will produce, this generative model. So we need to figure out how this looks like. And then we need to figure out a conjugate prior for that. That is to make math easy. Without conjugate priors, Bayesian inference, it's an absolute nightmare. I'm going to talk about what that means. That's particularly useful for any Bayesian inference, not necessarily LDA. Suppose you want to do Bayesian networks for games or something else. You want to have a conjugate prior because otherwise things get out of hand. And then we have to talk about sampling. Like in this process, there's a bunch of sample. Well, how do you actually do that? right? There's a bunch of things that are, I have to show you sampling techniques. And then, in particular, we need something called Gibbs sampling. That is, it achieves sample from joint, let's say P of xy. I give a distribution of two variables by iteratively sampling P of x given y and P of y given x. So this is a process that says you want to sample a joint distribution. That's too hard. But instead, you can sample the conditionals if you know them, x given y and y given x. In other words, says I want to sample a distribution of people and cars, joint two random variables. You know, people, I pick a person from, say, Boston, and car, I pick the car to give it to him or to buy it or something like that. Well, you can try to sample the pairs from the joint distribution. That often is very hard, especially if instead of two variables, I have 100. But instead, Gibbs sampling is a way to say, if you know the conditional, in other words, if you know, like if I tell you the car, what's the distribution of people that would buy that car? Like if I tell you the car, what's the probability of every person to buy that car? That's the conditional of people given the car. And the other conditional is if I tell you the person, him, what's the probability of him buying every single car? If I tell you those two conditionals, Gibbs sampling is a way to do this iteratively. All these sample distributions, most of them is not just producing one outcome. When I say roll a die or flip a coin, I mean multiple times. So they produce a sample that looks like the joint sample from the conditional. Extremely powerful technique, because almost always joint probabilities are a nightmare. But sometimes the conditionals are not. That's where Gibbs sampling applies. When you can get the conditional relatively easy, but the joint would have been impossible. And LDA is an example of that. You have a different exercise in Homework 5B, which talks about multidimensional Gaussian. So imagine I have a 2D Gaussian or 3D Gaussians. Remember those? We talk about those bells in 2D or 3D. Sampling from a 2D Gaussian is not that easy. Now, of course, MATLAB or Java have functions to do that. But it turns out that if you have a joint Gaussian, the conditional of x given y, y given x are also Gaussian distribution, unidimensional Gaussian distributions. So you could implement Gibbs sampling iteratively between conditionals and then end up with a sample of data points that looks like sample from the two-dimensional bell to start with. That's your exercise, one of the exercises in Homework 5B. To play with the Gaussian conditionals and obtain a sample that looks like sample from the joint distribution. So
should we be using a library for like Gibbs sampling?
you have to implement your own sampling, but I'll give you the formula for these distributions. So you have to iterate between them. I'll show you how to sample. There's a bunch of sampling techniques like inverse sample or reject sample, or we'll discuss those starting next time probably. But then you have to alternate x, y, y, x in order to produce the joint sample. So you implement your own Gibbs, but not solve the math of Gaussian math in here. That's some formulas that are given. But look at this list, huh? This is a monster list. And I should tell you an anecdote. I've taught this course many times. At the beginning of the course, we always start with the optimism, we'll be able this time to implement LDA. And that didn't happen until last summer. Okay? And the other sections of this course do start with the same optimism. Let's start with, I'll show you some beautiful slides, not created by me, by somebody else. Despite being beautiful, students will have absolutely no chance to implement LDA based on those slides. I mean, they tried. I know anecdotal stories of students from the other sections coming to my office hours and asking around, and after a lot of struggle, could not implement the LDA. And we tried that before and failed, but we're gonna succeed this time. Yeah, we have to go through this list here. One of the reasons is due to me and the TA's efforts to make this doable. We're gonna call it baby LDA because not the real LDA, but pretty close. But another reason is somebody got so frustrated with this. How can LDA be such a basic, simple thing, yet nobody can implement it correctly? They wrote a book, How to Implement LDA in Academia. So that's where we studied last summer that book and say, aha, that's the way to go. So in the next 2 lectures and a half, whatever is 2 lectures, our job is gonna be to work through this list to the point that you guys do 5B, homework 5B. And if that requires another lecture after Thanksgiving, I'm happy to sit on it until we actually get it done conceptually and programmatically, but programmatically won't be a big deal. Once I show you what this whole theory comes down to in code, you're gonna be like, just give me the pseudocode and I'll write it up, and it's not gonna take that long to work it. But we have to understand why that works. So for now, what I would like to do today is to start looking at this part. I'm gonna ignore alpha and beta a little bit for now. I'm gonna say, okay, what's up with these documents? But when I say documents, I don't mean the actual documents. I mean the documents that are coming out of this generative model. So of the generative model, I pick a topic, right? Say I have a document and it has, I don't know, 10 words in it. For every word, I have to pick a topic, and from that topic, I will, so I'm gonna move somewhere here. And I say, how do I think of a topic of a generative document? Generate a document for n equal, say, 10, for I equal 1 to 10, right? Select topic according to probabilities. I think we call those betas. And then select word, let's call W. So select topic VK according to, I call it proportional with. Actually, it's not proportional, it's sample by probabilities, sample probabilities of beta, and select word I think in the notes is Z, according to sample probability of that topic.
Why is sampling hard? Like, why can't we just like put everything over a range to 100 and then like pick a random number and then like there's our topic and then do a range of 1 to 50,000, roll a dice,
Right.
take
So
that.
that's a particular sampling technique.
Okay.
It's a discretization of the probability space. In fact, we don't have to discretize it to do what you're saying. So we're going to talk about sampling next time. What he is saying, in effect, I think, is saying if I have a PDF stands for
Probability distribution function.
or density or distribution,
Density,
and CDF stands for cumulative distribution function. So if I have a cumulative distribution functions, this is all my outcomes. And say sorted by probability, but it doesn't matter what, in some order, right? So outcome 1, outcome 2, outcome T. This is called the sampling space. It's like when you roll a die, you have 6 outcomes. And then this is the cumulative distribution. It does something, but eventually reaches 1. Right? So for any particular, if these are outcomes are sorted, this is outcome X. This is the probability of anything of, so this, let's call it a parameter like T. Probability of X more equal than T, if this is sorted. Right? It's everything up to t. What his proposal is, well, he talks about inversing the CDF. I think you mean pick a random from 0 to 1, random r here, and then try to go see where you end up on this line. So I have multiple questions about that. One would be, would this correspond to the actual correct probability? That's a theoretical question. And then I have a practical question. How do I inverse the CDF? Like if this was a Gaussian, this CDF for Gaussian is a monster, right? So how do you pick picking a random number? This is random uniform, I'm assuming, right? I want a random uniform R, but then how do I reverse the CDF if this is if it's a discrete distribution like a die, I think it's a stair thingy, right? In a die will be 1, 6, 2, 6, 3, 6 if it's uniform. But if it's not uniform, will be whatever the probabilities are. So if this is a stair, like a die, let's say the 1 is this probability, right? And then 2, 3, 4, 5, 6. Then it sums up 3, 4, 5. See, this is not uniform. You can tell the 6 has this probability here, right? But the 5 has a much smaller probability. So in here, if I pick a random R uniform, probably gonna do some sort of binary search. In this CDF, this is P of 1. This in here is P1 plus P2. This in here is P1 plus P2 plus P3. This in here is P1 plus P2 plus P3 plus P4 plus P5, right? Because it's cumulative density. So if you pick an R, and this is definitely sorted, CDFs only goes up because they keep adding probabilities. You have to do a binary search between the CDF values. That will be the way to find out where you are. I wanted to save this for last time, but since you asked, there's a bunch of techniques for how to do this. And some of this sampling that's needed, it's actually very complicated. Some of it is not. Right? So let's leave this for Friday. How to deal with sampling. And we're going to talk more about just this sampling, so you guys have a little bit of background into if I really want to sample a die, how do I do it other than picking die and roll it and see what happens? Like if I want to really want to do something with these distributions. So I'm going to simplify things a lot here in order to create an intuition at first. And I'm going to say, let's say I have n trials, which corresponds to the length of the document. And every word is either 0 or 1, a binary. So my n and the outcome for n equal 10 might be 0, 0, 0, 1, 0, 1, 0, 0, 1, 0. 3, 3, 3, 1. 10 of them, right? So I'm taking a very simple case where every word, I don't have 50,000 words, I only have 2 words. Every word is either a 0 or a 1. Sometimes people prefer to call this heads and tail. But here's the thing. Every word is generated by a coin selected for that word. Binary words are called flips because people think of a coin It could be heads or tails, and it's either head is 1, tail is 0, right? So we call those flips, and the generating mechanism is throwing the coin in the air, right? It's generated by, very important, coin selected for that word. So I don't use the same coin here. I have k coins. Because I want to simulate this process here. So how this goes, I know I'm going to need 10 flips or 10 words. I have k coins. Let's think of k equal, I don't know, 5 or 3. What do I do? For every word, I select a coin, and then I use that coin to flip it in the air to see if I get a head or tail. Now, they have different probabilities. Now, a coin has only 2 probabilities. Every coin has either tail or heads, right? So this is called probability of head is the probability of 1, which we call it P, for that coin. And probability of tail is the probability of 0 is 1 minus P. It's effectively this matrix with D equal 2. There's only 2 things. So every one of these topics, they're coin nouns, it's going to be a P to get a head or 1, and a 1 minus P to get a 0. But it's not the same P. Different coins have different probabilities, right? So every coin has a probability, but not the same. Okay? And then, let me find some notes here. So then, this P, I don't know the P, right? So I have 3 coins, but I don't know what probabilities they have. Can you believe that? So what I know I have a prior. So P is unknown. I do have 3 coins. I can see them in front of me, but I don't know what probability of heads they get. I can flip them, perhaps to generate these sequences of n equal 10 things, and then if I flip them enough, I'll find out something about those probabilities. So I have a prior of how P is a sample from a distribution of parameters. I'm going to leave it at that for now. And I'm going to say, here's what happens with my document. So I'm back to this document, which is a sequence of n flips. Now, I'm going to introduce the binomial distribution, which is x is a count given n and p. In English is the probability to get x heads out of n trials with coin P. By P I mean P is the probability of heads. So if I fix a coin, right, and I tell you I flip it 100 times, and I tell you P this time, P is 30% chance of heads. What's the chance of getting 45 heads? So again, what am I doing here? I have a P that's fixed, You see, notice after this bar means we know these guys. When probabilities, when we put a bar means we want this given the other two. So we know we run it 100 trials. We know the probability of a heads is 30%. We know the expected number of heads, like could be 30% times how many trials you make. But what's the chance of a particular number of heads, like say 45 or 25 heads? That's the binomial distribution. This is n, choose x, p at x, 1 minus p at 1 minus x. Sorry, n minus x. Now you guys know the n choose, that's n factorial, x factorial, n minus x factorial, right? That's the n choose x times p at x times 1 minus p at n minus x. This is the binomial formula that I think most of you have seen. That has to do with if you do n trials, in every trial you have a p chance to get a head and a 1 minus p head chance to get a tail. So if you think of head plus tail probabilities, head plus tail, n, this is n trials here. And how many ways can I get exactly x heads? Well, out of these n parentheses, x of them have to be the head. The other n minus x have to be the tails. So the p at x stands for, you gotta get with probability p x heads. So that's p times p times p times p x times. This is 1 minus p, that is the property of a tail at how many tails I got. And the n choose x is in how many ways can I choose x parentheses to give me the head out of n of them. It could be this one, could be that one, could be that one. So in how many ways can I choose out of n parentheses x to select the heads? Binomial formula. So now we want in here a distribution for mathematical purposes that is the conjugate prior to that, to binomial. I'll describe that it means in a second. That is going to be the beta distribution. So if we start with this model, where is this coming from? This is coming to say, well, you want that many heads, x heads. This is, if you generate the flips independently, you're going to have p times p times p times p x times, and 1 minus p, those are the tails, 1 minus p, 1 minus p, the other n minus x times. This is 45, this is 55. And in how many ways can I pick which 45 are the heads and which 55 are the tails? Could be the first 45, could be that 45, that's how many ways can you pick 45 out of 100. So that's the probability. You should know that these numbers sum to 1. If you sum it over all possible x's, you get probability of 0 heads, 1 head, 2 heads, up to n heads. Of course, those have to sum to 1. So that's the binomial formula. If you are to sum up for all x's from 0 to n choose x times p of x, 1 minus p as 1 minus x, you would get p plus 1 minus p at n. That's the binomial formula. Remember in high school? No? I think people should do this in high school, the binomial formula. And then how much is p plus 1 minus p? 1 at n, that's 1. So that is a distribution. These numbers sum up to 1. It's a binomial distribution. And we want the prior. Here's why we want the prior. So I'm going to say x1, x2, xn are IIDs, where every xi is a Bernoulli of P. Bernoulli, it's a fancy name that stands for something very simple. The probability of 1 is P, probability of 0 is 1 minus P. That's called a Bernoulli trial. So when you hear this name Bernoulli, it's a fancy name that means you have a 30% chance to get a head and 70% chance to get a tail. So suppose I do this, right? I flip this with various coins. That's my sequence. Each one of them is 1 or 0. Because it's either head or tails. These are my N flips. What we want to do, this is a prior of P. This P, the coins distributions onto heads and tails. This is a posterior of P, which is kind of combined prior plus evidence. So in here I'm going to say how many heads do I have. I can observe that. And in here I'm going to be like, I need this beta distribution. So here's the beta of P given, there's two parameters here. Let's call them alpha. I don't want to do alpha and beta because the beta means something else in there. Let's say A and B. This is A plus B minus 1 factorial divided by A minus 1 factorial. Looks like that one, but it's not. People are confused between this distribution and that distribution because they look so similar. You see the P at X and you can think of X being A minus 1 and N minus X being B minus 1, but don't be confused in here of the following. This is a distribution in X. The probability is on X. What is the chance for X to be 45? So you see when I sum up to get 1, I sum up over X's. This is not a distribution in A and B, which stands for the X's in here. This is a distribution over P. So P is that chance of getting ahead. So what is my chance for that P to be, I don't know, 20%? I plug that 20% in here, I get the value. What is the chance of P to be 50%? I plug that P in here, I get the value. A and B are fixed here. So this A and B, the way I want you to think of them is A and B, N minus 1 and B minus 1, are prior counts of 1, 0 in all data. So the beta distribution corresponds to saying how many heads and tails you've seen so far in all the flips that you've done in the past. You've seen that many heads and that many tails across again, like you look in a prior training set or something. This beta is telling you what's the chance for the coin used to do those flips to be 20%, 30%, 60%, so on and so forth. Now, any P it's possible, right? I can have a P, a particular outcome of flipping coins could be obtained with a P that's, say, 10% chance of heads or 90% chance of heads. But that's more or less likely. If I have a lot of heads, chances are my coins have more probabilities on the heads. But it's possible, with small probability, that the coin that's biased towards tail to have produced that data. Because when you flip it, it's possible to come out with the low probabilities. So this is telling me, if you look at, roughly speaking, in the past, how many heads and tails you observed, A and B? This is kind of the probability that your coins that you use have, say, a 50-50 bias, or a 40-60 bias, or a 70-30 bias, right? When A equal B, the most chance will be on P equal 50%. So why is this the distribution? We could use a different distribution. This we impose as a model. The only one that's natural, that has a natural explanation, is this one that says if your flips were generated independently from these coins, you would observe something like this, because this is the binomial distribution. So the way we use this is to say, here's how we think of, we start with a P that's accordingly distributed this way as a prior. But then we flip it n times, the coins, the k coins we have, and we getting a particular sequence of heads and tails. Right? So what is the posterior probability of P? I'm going to call x bar the sequence of heads and tails. So now I have the data, but also where I started, A and B. So now posterior means I assume in the beginning it's like that, maybe 50-50. Maybe the total number of heads and tails was 50-50, so I assume this is the distribution. I don't mean P is 50%. It's a distribution that has the maximum probability on 50%. Because it could be 60-40 and still get equal heads and tails. And now I'm asking again, now what do you think about this P of the coins after you started with those assumptions, but you now notice how many actual heads and tails you see in the current data? So this is proportional. So it's probability of x given P and A and B times the probability of P given A and B divided by probability of x. Right? It's kind of a Bayes formula here, because I want P given x, but I'm going to do x given P. So how is this going to go? This is the proportional again. Like I'm skipping the constant. The product of P at this xi from I equal 1 to n, 1 minus P at 1 minus xi, P at A minus 1, 1 minus P at B minus 1. So why is that? Because the probability of x, it's going to be something like this, right? And probability of P is going to be something like this. I'm skipping some details here to keep the intuition flowing. And then some other time we can actually plug in all the combinatorials and see how it works. I'm not that interested in you understanding the math, all exact derivations. That's way too difficult if you have not seen this already. If you see it for the first time, I care about more like, why are you picking this distribution in particular for this evidence kind of observation of data? Here's why. When you do this thing, this is a parenthesis here, the product only goes on these i's. This is proportional with P at, this is sum of xi plus A minus 1, because this P multiplies with this piece in here. It's sum of the xi's due to the product sums up the exponents, plus A minus 1. And then 1 minus P times n minus, this is n, 1 minus xi, when you sum them up, is n minus sum of xi, plus B minus 1, that's coming from here. And that's effectively a beta distribution of P given new parameters. Given the original parameter A, but now with sum of xi, and the original parameter B plus n minus sum of xi. I skipped a lot of things, so a lot of this is incorrect for now. Next time we'll do it correctly. I skipped these factorials. I only put proportional P's because I'm saying probability of X, first of all, doesn't matter here. Data is fixed. So whatever you observe, so that doesn't matter. But then I skip some of the factorials. I say proportional with, kind of wishful thinking. But what's my point here? Intuitively, I was assuming that P is distributed in a certain way, beta distribution, according to previous counts. This is the count of how many heads I've seen. This is the count of how many tails I've seen. Now what happens? I roll it n equal 100 times, and I notice heads 45, tail 55, let's say. What is my new belief distribution of P? Is the one I started with, A, how many previous heads you've seen, plus how many heads you've seen right now. It's like kind of saying you have a training set with A heads, and you're adding to that training set, the sum of xi will be how many heads I got in this current batch, right? Because every xi corresponds to 1 for a head. If you sum up how many xi's are 1, you get 45 heads. And what happened here? This is the how many tails you've got before and how many tails you got right now, right? Because n minus sum of the xi will be number of tails. And this will be the number of heads. So my point is, why did we pick this distribution? This distribution evolves very naturally into the same family of distribution, the beta distribution, which has a formula. But the formula is not important right now. That if you say, okay, that's how I start initially assuming heads versus tail. When I flip these coins, the K coins I have, another 100 times, another 1,000 times, if they came up with a number of heads and tails, my new belief in the distribution of the possible biases of these K coins change accordingly to now my new number of heads, which is the previous one plus the current ones, and the new number of tails, which is the previous one plus what I've seen right now. So my structural belief in P didn't change. It's just the number of heads and tails that have changed. I still believe the P, the bias of the coin, is distributed according to the beta function. But now my beta has updated because I've seen more heads and tails. You guys don't believe me.
How are you getting the xi's again?
Xi's are 1 or 0. For each trial, 1 is a head, 0 is a tail.
So a trial is where you're selecting from the...
Right, so the reason is a product here is because you get the probability of heads for every head. For every time this x is 1, and you get the probability of a tail for every tail every time x is 0. Every xi 0 is a tail, every xi 1 is a head. So there's multiple incorrect steps in here. If you go home and study, you're going to see different things, which I intend to fix. But I don't want to lose the common sense. This is really not factorials. It's a function that generalizes the factorial, so-called the gamma function. So it's an expansion of factorials into continuous space. So we want to be able to do these factorials even if a is 2.5. But it's easier to see it as factorials for now. We're going to replace that with the gamma function. And this beta is called the conjugate prior of the binomial distribution, because if you start with that prior believing the bias of the coins, the P's, and you see evidence according to binomial distributions, which is what will happen if the flip of the coins are IID, we're going to get the binomial distribution. Then the new belief in P, what we believe the bias of the coin is, it's still a beta function, because the arithmetics work out to be exactly the same function like before, except with updated counts. Now, an additional, very intuitively easy to buy benefit is how much the prior matters versus the evidence. If A and B are very big counts, let's say 50-50, I've seen it before 1 trillion times, then the evidence likely not going to change my belief, right? If A is 500 billion and B is 500 billion, even if you flip it another 100 or 1,000 times, these new counts, A plus the heads, B plus the tails, will still be pretty equal. So you're not gonna change my belief. You'll have to flip it a big number of times to change my belief. On the other hand, if A and B, the previous counts in absolute terms, are small, like I only see 2 heads and 2 tails, I flip the coin 4 times. That's called a weak prior because I don't base it on, in absolute terms, A and B very small means I don't have a lot of prior training data. Then if I flip this 1,000 times, this plus this will be 1,000. A and B, the original A and B won't make any difference, right? If this comes out 700 versus 300, what's 702 versus 302? So the amount in A and B is not just the proportion of heads versus tail, is in absolute terms how strong the prior is. If large A and B's indicate a very strong prior, that will persist until you flip this millions of times, as opposed to small counts A and B indicate a weak prior that will change very quickly with the evidence. As soon as you flip that coin a bunch of times and you notice it's like 70-30, 70% heads, even if the prior was 50-50, you're still gonna believe quickly it's 70-30. But with big A and B's, it will take a lot of flips to change my mind. This has a lot to do with when do you think a coin is, or a die roll is faked? How much evidence do you need to see to start changing your belief that the coin was not fair, 50-50? It depends on how strong the prior is when you start. Now, this whole story, next time, will also work not with 2 categories, aka 0 and 1, but with 50,000 categories, which are our words. Our words are not 0 or 1, are a selection from 50,000 or 100,000, how big the vocabulary is. So we're not gonna have 2 possibilities for selection. We're gonna have 50,000 possibilities. This is gonna be called multinomial, which is the same distribution, but X is not just heads or tail. It's gonna be 50,000 possibilities. So the counts I'm getting here, how many heads, how many tails, is gonna be how many of that category, how many of that category, how many of that category, up to 50,000 categories. And this dude here, beta, becomes a Dirichlet. So it's the same exact function, but it's not just with 2 things, heads and tails. It's with the prior counts of all categories. So we're gonna keep going with the binary world to understand this one perfectly correct. And then we're gonna say, let's hope the whole thing works in multidimensional just like it works in binary. So instead of binomial and beta, which we're gonna do in more detail, we're gonna see what happened to these combinatorics and factorials, where did they go? But then we're gonna say, okay, hopefully that works the same way for multinomial and Dirichlet. So that will explain how come these 2 parts work. What do we think of a generative model will be the multinomial distribution, the conjugate prior will be Dirichlet. If you only have 2 possible words, that will be beta and binomial. But then we have to talk about sampling. How do you actually make this work? Because every time we say sample a document, sample a topic, sample a word, theoretically means pick something from that distribution, but in practice we have to write a computer program that does that. All right. So I'm going to stop here. Obviously, we're going to continue. I'll keep the camera on if you have any questions. Let's talk about this. I know I'm over. Next time I'll be over, and next time I'll be over again. Sorry about that. I want to get some theory that makes sense. I don't want to go too far into the math and theory when we start losing sense of it. But then if that's a little bit non-rigorous, we can live with that. It's not so rigorous, but at least we understand what this stuff means. And then I'll give you a script for LDA, which will make sense, and it's not so hard to implement, that requires all these parts in here. But that's not for 5A. For 5A, you can just call it LDA library. I'll show it to you next time. Beautiful, works perfectly, spits out the topics and all the probabilities. All right, are we good? Close this down there.